We're now going to study the unit circle a little bit more and see how it extends I guess we could say the traditional SOHCAHTOA definitions of functions, and how we can actually use it to solve for angles that the SOHCAHTOA definition of the trig functions actually doesn't help us with. So let's just, as a review, remember what SOHCAHTOA told us. It told us, or with that definition, I'll write it up here in this corner. I don't know how let's see, so I don't want to get confusing because I don't want to write over too much. SOHCAHTOA. And that told us, I'm sorry, I got it all jumbled up here. But that told us that sine, if we have a right angle, that the sine of an angle in the right angle is equal to the opposite side over the hypotenuse. The cosine of an angle is equal to the adjacent side over hypotenuse. And the tangent side is equal to the opposite over the adjacent side. And this worked fine for us, but if you think about it, what happens when that angle approaches 90 degrees? Because you can't have two 90-degree angles in a right angle. Or what happens when that angle is greater than 90 degrees? Or what if it went negative? And that's why, if you remember from the previous video, why we needed the unit circle definition. So let's review the unit circle definition. Let me erase this. Dum-da-dum-da-dum. I hope you can. Let me erase. I actually got this unit circle. I think I got it from Wikipedia, but I want to give due credit to whoever I did get it for, this drawing of the unit circle. But the unit circle kind of extends that SOHCAHTOA definition. It tells us that if we have a unit circle, and this is a picture of a unit circle here, a unit circle is just a circle centered at the origin, centered at the point 0, 0, and it has a radius of 1, so it intersects the x-axis at 1, 0, and negative 1, 0. It intersects the y-axis at 0, 1, and 0, negative 1. If we have a unit circle, we define, let's just say, let's start with the cosine of theta. We define the cosine of theta as, let's take an angle that's between two radiuses in this unit circle. And one radius is going to be the positive x-axis between 0 and 1. So one radius is going to be this line here. And then we have the angle is the angle between that big you could kind of view that as the base radius and some other radius. So let's say this case right here. And this would be our angle. The unit circle definition tells us that the cosine of this angle is equal to the x-coordinate where this radius intersects the unit circle. And that the sine of this function is equal to the y-coordinate where this point intersects the unit circle. So for example, in this case, if you can read behind my line, this says 30 degrees equals pi over 6. So this angle right here is 30 degrees, or pi over 6 radians. Pi over 6 radians. And what this definition tells us is that the sine of 30 degrees is 1/2, and that the cosine of 30 degrees is square root of 3 over 2. And what I want to show you is that this unit circle definition actually coincides with our SOHCAHTOA definition, but then it extends it. So let's see how we can get from that SOHCAHTOA definition to this unit circle definition and why they're actually consistent with each other. So let me erase some of what I have written here. Let me get the eraser tool. I'm going to erase what I had. So let me go back to the pen tool, make it small again. Okay, I think I'm all set. So let's go back to that theta. Let's say that this is the theta, and as we said, this angle is 30 degrees or pi over 6. Let's drop a line from that point to the x-axis. And as we see, this line is perpendicular, so this is a 90-degree angle. This is a 90-degree angle. And if this is a 30-degree angle here, this is 30, right? Theta equals 30. That says theta equals 30. This is 30, this is 90. What is this angle? Well, this is a 60-degree angle, right? Because they add up to 180. So this is a 30, 60, 90 triangle. Interesting. And what do you remember about 30, 60, 90 triangles? Well, the side opposite the 30-degree side is 1/2 the length of the hypotenuse. I hope you remember that. I don't want to confuse you too much. So this is the side opposite the 30-degree side, right? And what's the hypotenuse? This is the hypotenuse. And what's the length of this hypotenuse? Well, it's 1, because this is a unit circle and this is a radius of the unit circle. So the length of this hypotenuse is 1, and so the length of this side, which is opposite the 30-degree angle, is going to be 1/2, right? And I'm just using the 30, 60, 90 triangles that we've done previous videos on. And what's the side opposite the 60-degree side? Well, once again, it's square root of 3 over 2 times the hypotenuse. And so it's square root of 3 over 2, right? So we can figure out that this side is square root of 3 over 2, and that this side is 1/2. So a couple of things we can figure out. Just by looking at this, we can immediately say, well, what's the coordinate of this point? Well, its x-coordinate is right here, right? Its x-coordinate would be square root of 3 over 2. That's this right here, this distance. And its y-coordinate would be the length of this side of the right triangle, or 1/2. And there we have it right here. It was already written for us. The x-coordinate is square root of 3 over 2, and the y-coordinate is 1/2. And now what I want to show you is why this x-coordinate can be taken as the cosine of theta, and why this y-coordinate can be taken as the sine of theta. Well, what does SOHCAHTOA tell us? Well, let's start with the cosine. So SOHCAHTOA. So SOHCAHTOA. Cosine is adjacent over hypotenuse, right? Cosine is equal to adjacent over hypotenuse. Well, in this triangle I just drew, what is the adjacent side to this angle, right? Because we're trying to figure out the cosine of this angle, this 30 degrees. Well, the adjacent side to this angle is, of course, this side, right? So adjacent is square root of 3 over 2. We figured that out just now. And what's the hypotenuse? Well, the hypotenuse is this side, right? Which has length 1, because it's a unit circle, and that's a radius of it. So the cosine of this angle, using the SOHCAHTOA definition, is square root of 3, the adjacent side, over the hypotenuse, 1. So square root of 3 over 2 over 1, which is the square root of 3 over 2, which was the same thing as the x-coordinate. Similarly, we could look at sine. Sine equals opposite over hypotenuse. Sine equals opposite over hypotenuse. Well, what's the opposite side? It's 1/2, and the hypotenuse is 1 here. So the sine is just 1/2 over 1. And so we have it here. And so that's why the unit circle definition isn't kind of a replacing definition for the SOHCAHTOA definition. It's really just an extension that allows us, I mean, for 30 degrees SOHCAHTOA worked, for 45 degrees SOHCAHTOA worked, whereas for 60 degrees it would work. But once you get to 90, it becomes a little bit more difficult, right? If you use traditional SOHCAHTOA and you try to draw a right triangle that has two 90-degree angles in it, because you couldn't. And especially once you get to angles that are larger than 90, or angles that actually could even go negative. It's not drawn here in the unit circle, but 330 degrees is the same thing as negative 30 degrees, because you could go either way in the circle, and you could keep going around the circle. You could figure out the sine or the cosine of, 1,000,000 degrees if you just keep going around the circle. So hopefully this gives you a sense of the unit circle definition of the sine and cosine functions. And of course the tangent function is always just the sine over the cosine or the y over the x. And you could use the unit circle definition for that as well. And I'll leave it for you as an exercise to try to derive all of these other values using this unit circle and using what you already know about 30, 60, 90 triangles, and what you already know about 45, 45, 90 triangles, or what you already know about the Pythagorean theorem. And you should be able to figure out all of these values going around the unit circle. Hopefully that was helpful. See you soon.